All right, this is the final video in a four-part series on conic sections. We've already talked about circles, ellipses, and parabolas, and right now we're going to talk about hyperbolas. What happens if you slice these two cones perpendicular to the base and the two curves that result, the two branches that result. Now, they look similar to a parabola, but a hyperbola actually is a little bit wider. It sort of extends outward a little bit more, so it does create a little bit different shape. And in fact, those two branches that extend outward are guided by a couple of asymptotes, and we'll talk about those in a minute. But the main idea behind the geometric definition of a hyperbola, or the locus definition, similar to an ellipse, is that the distance from a focus to any point on the hyperbola and the distance from the other focus to that point, this time will be the difference, which will be constant. For an ellipse, remember that it was the sum of those two distances were always the same. Now it's going to be the difference. So again, that D2 gets a little bit longer as we kind of move farther down the hyperbola, but so does D1, and the difference between them will still remain constant. Now, there is a couple of lines of symmetry. There would be a line of symmetry running up and down on this picture, but also there's a line of symmetry that runs through the foci, also through the vertices. And for a hyperbola, we call that the transverse axis. It sort of transects, or it kind of cuts the two branches, through those vertices. Now, some of the definitions for a hyperbola, again, also very similar to an ellipse. You'll notice that the overall equation is very similar. The one major difference, pun intended, is that it's now a subtraction, not a sum, not an addition symbol in the middle. We're now finding the difference between x squared and y squared to give us 1. A squared will always be in the front this time. A is not always necessarily greater than b, as it was for an ellipse. A squared will always be in the front or in the positive fraction. B squared will always be in the second fraction. It's all about whether or not x squared minus y squared is present. And if that's the case, the front part being x squared means we're going to have a horizontal transverse axis. Or if we switch over to this picture, notice we can have a hyperbola going up and down, but now y squared will be minus x squared. For both pictures, a squared plus b squared equals c squared. We're right back to sort of a nice Pythagorean theorem defining, again, our picture here. So a squared plus b squared equals c squared. Now, the reason we get the picture that we do is if we travel from the center, a units, still going to find us those vertices being a units from the center. B units will travel left and right for our vertical picture here, our transverse axis traveling north and south. So again, our foci and our vertices all on the y-axis. B will be on the x-axis. However, B doesn't determine any points on our actual hyperbola. A and B determine sort of this box that is formed. And the corners of that box, if we draw a couple of diagonals, you'll notice these nice long dashed lines, are what we call the asymptotes. The hyperbola will be sort of boxed in. It's going to run through the vertex, around the focus as usual, but it's going to guide along the asymptote, again, infinitely close to it, but never quite touching. That's what an asymptote is, infinitely close, but never quite touching there. Go through the vertex and then coast back out here again toward the asymptote. You'll notice the same thing happened for the horizontal axis. Again, B was up and down, A was left and right. We draw that nice little box there. Dashed lines through the corners. And again, the asymptotes are determined, so we can follow the asymptote through the vertex, up again along that asymptote. To determine the equation of the asymptotes, just realize that it's all about rise over run. If we're going left and right, if we have a horizontal transverse axis, then A is the run. It's going to be our left and right, our x value. B is our rise. So to get those lines on there, basically plus or minus B over A. If we're talking about vertical, it's plus or minus A over B. A is now the vertical or the rise. B is the run. And again, we're always going through the origin, so we don't need to worry about any plus a y-intercept out here. It's just slope times x. But we do get both a positive and a negative line. So again, the two major things we want to do with conic sections, we want to be able to graph. We also want to be able to find the equation. So again, similar to all of our other equations, I'm going to take my look at this and say, okay, I have y squared minus x squared. That immediately tells me that I'm going to be traveling vertically, right? Y squared minus x squared, we're going to be traveling vertically on that transverse axis, but I would rather be equal to 1 over here on the right side. So I'm going to divide everything by 36. Our front number always determines our vertices, right? So that 4 in front, a will equal 2, and our vertices will be 0 plus or minus 2, again along the y-axis. The second number is always b squared, so b is 3, which again doesn't really determine any points, but it's going to help us define that box. So we could immediately take our asymptotes, we could go draw this little orange box, right? 2 units up and down for the a value. So our vertices will fall right on those points. B, again, is going to go left and right, not necessarily points on the hyperbola, right? But they'll be there. And the foci, again, we've got a squared plus b squared equals c squared. So plug everything into our formula. 4 plus 9 is 13. Square root is about 3.606. And so we can put our foci up about 3.6 and down about negative 3.6 on our graph. After that, it's just a matter of drawing our hyperbola and maybe determining the equation of the asymptotes. Remember, rise over run says a is the rise, b is the run, so 2 over 3, and we've got the equations there. And after that, it just comes down to drawing our line. And in that case, you just kind of coast along here, follow out to the asymptotes. If you get a little too close, it's not a horrible idea. Not the most symmetrical of hyperbolas I've ever drawn. Sometimes it helps to just draw the whole picture all at once. A little bit better. Hopefully your hyperbolas look a little bit smoother than mine. Make sure you run through the vertice, and again, follow the asymptotes after that. If they give you information and you want to determine the equation of a hyperbola, again, the major idea is we need to have a and b, and we need to know vertical or horizontal. So if we're looking at the vertices and x is going plus and minus 3, then we're traveling horizontally on the transverse axis. We're going to put x squared before y squared, x squared minus y squared in the formula. We also know then that a is 3. If they give us the foci, we know that c is 4. So we've got c squared and a squared. We can use those to find our b squared. Again, a squared plus b squared equals c squared. Feel free to pause the video if you need a second to kind of ingest all that. But basically, if we have a squared and b squared, we've got how we're going to shape our formula. We can plug those all in. And x squared over a squared minus y squared over b squared equals 1. Again, feel free to go back and review the video or pause at any point if you need to. If you have any questions, talk to your teacher. And otherwise, happy graphing.